The basic DC motor, like the DC generator, consists of a pair of magnetic poles, an armature made up of a single turn loop, a commutator, and a brush assembly. As we have seen, a conductor in a magnetic field will move when a voltage is applied to it. With a voltage applied and the magnetic field and current flow as shown, the right conductor will be pushed down, while the left one is pushed up. Since the forces on each conductor are now in exact balance, there will be no more motion. Adding another loop and two commutator segments ensures that at no time will balancing forces cancel each other out. With this setup, there will be motion at all times. As one commutator segment is moved away from the brushes, another now takes its place and the movement continues. The greater the number of loops in the armature, the smoother its motion. For this reason, rotors in practical DC motors have many loops. Since current in the rotor loops must reverse each half cycle, two commutator segments per loop are required. Here in the motor, as in the DC generator, there is a neutral plane. The interaction of the conductor fields on the main field causes this neutral plane to shift and sparking to occur when a load is added. Sparking in DC motors also produces burned commutators and interference in nearby electronic equipment. This sparking can be prevented in one of two ways. One is by the adjustment of the brush position. The brushes are moved until they lie in the adjusted neutral plane. In the motor, as in the generator, small interpoles between the poles of the main magnets are also used to eliminate the shift of the neutral plane. These interpole fields tend to oppose the fields created by armature reaction. The neutral plane is moved back toward its correct position. Also aiding are compensating windings, which carry armature current in the opposite direction to the current in the armature conductors. The neutral plane is thus maintained in its proper position. DC motors operate most efficiently when sparking is eliminated. We saw earlier that when a conductor is moved by mechanical energy in a magnetic field, an EMF is generated. This is generator action. In the DC motor, when rotation is desired, it is necessary to apply an EMF to the conductor. However, when used as a motor, an opposing EMF is also generated in the conductor. This is called the counter-electromotive force, or CEMF. By Lenz's law, the generated CEMF must oppose the applied EMF. The amount of CEMF depends on the speed of rotation. This is of practical importance in large motors. When starting large motors, the problem exists of limiting current through the rotor windings until a CEMF can be built up. If the full current is applied before the CEMF develops, it may burn out the rotor windings. Starting boxes are used with DC motors in order to avoid this application of current before the CEMF is built up. Here is a basic shunt motor with its starting box. In the starting position, the circuit to the rotor windings is closed through a series of large resistance coils. As the lever of the switch is moved, rotor speed and CEMF build up gradually, and the resistance coils are subsequently cut out until running speed has been reached. The lever is held in the fully open position by an electromagnet. If for any reason the power should fail or the field coil open, the electromagnet becomes de-energized and the lever is returned to the starting position by spring action. Just as in DC generators, DC motors seldom use permanent magnets for the field. Instead, electromagnets are used. Like with a DC generator, field windings are constructed in several ways. Each type of winding has special characteristics, special values, and specific uses. The series wound motor has good starting torque or turning force. Torque depends on armature current and on field strength. Since field strength is proportional to current, the high starting current before CEMF is developed affects torque as the square of the current. The motor begins to turn, attempting to develop enough CEMF to completely oppose the applied EMF. The load prevents this, acting to control the speed of the motor. But if the load is suddenly removed, like in the case of a broken belt, the motor will build up speed trying to develop more CEMF until it destroys itself. The desirable characteristics of both the series and shunt wound motors can be achieved in the compound wound motor. In order to obtain good starting torque, the series field is used. When running speed has been attained, a centrifugal switch cuts out the series field and cuts in the shunt field. It is now a shunt motor and the speed regulation is good. Compounding provides good starting torque and good speed regulation. This allows for efficient operation and minimizes the possibility of damage to the motor. But because the movement of the conductor in the field is actually circular, we must also multiply with a sine of the angle formed by the lines of force and motion of the conductor in order to arrive at the EMF. All generators are basically alternating current generators and produce AC internally. The basic AC generator becomes a DC generator when a commutator is attached to the conductor. Each commutator segment rotates with its respective conductor, producing a direct current. This current, which is a pulsating current, is made smoother by the addition of more magnets and more loops.